In question 1, we've got the histogram here showing the times taken t minutes by each of 100 people to swim 500 meters. And we need to use the histogram to find the missing frequencies in the frequency table given. Well, we know that in a histogram, the area is proportional to the frequency. So I will start by scaling the frequency density axis. So maybe this is 1, this is 2, this is 3. And I will calculate the corresponding area for each of the shaded bars. The first one over here has a width of 5 and a height of 1. So its area is 5 times 1, which is 5. The next one has a width of 4 times a height of 2, which is 8. Then it's 4 times 3, which is 12. Then it's 7 times 2.5, which is 17.5. And the last one has a width of 15 times 0.5, which gives an answer of 7.5. And we said that the frequency is proportional to the area. So I'm just going to write down below each frequency the corresponding areas we just found. So for the first class here with a frequency of 10, the area was 5. Then it was 8, then it was 12. So we can see the relationship here. The area times 2 will give me the frequency. Proceeding for the 18 to 25, we had an area of 17.5. If I multiply this by 2, I get 35. So that's the frequency. And for the last class, it's an area of 7.5. Multiply that by 2, you get 15. So the frequency for the 25 to 40 class is 15. Now in part B, we need to estimate the number of people who took less than 16 minutes to swim those 500 meters. So less than 16 minutes means surely these 10 people, these 16 people, and observe that the 16 is halfway between the 14 and the 18. So I'm just going to take half of the frequency in the corresponding class. So I'm just going to take 12. So to find the missing number, it's going to be 10 plus 16 plus a half of 24, and this gives an answer of 38 people. In part C, we are asked to find an estimate for the mean time taken to swim the 500 meters. So we've got the time taken and the corresponding frequencies. I'm going to use the midpoint to estimate each of the class because we're looking at the grouped frequency table. So the midpoint of 5 and 10 is 7.5. The midpoint of 10 to 14 is 12, then it's 16, then it's 21.5, and then 32.5. And to find an estimate for the mean, t bar, it's going to be sum of fx over sum of f. So I'm multiplying frequency by midpoint and adding up. So it's going to be 10 times 7.5 plus 16 times 12 plus 24 times 16 plus 35 times 21.5 plus the 15 times the 32.5, and we know that we've got a total of 100 swimmers, so divide that by 100, we get an answer of 18.91 seconds. It's a good idea to include the units with your answer. And then in part D, we are told that the sigma ft squared is 41,033, and we need to work out an estimate for the standard deviation. Well, we know the formula for the standard deviation being the square root of sigma ft squared over sigma f minus essentially the mean squared. So in our case, it's going to be 41,033 over 100 minus 18.91 squared. This is the variance. If I take the square root, I'll be getting the standard deviation. It works out to be 7.26 seconds. Again, remember that the units in which the standard deviation is being measured are exactly the same units as the quantity we are measuring. So we've got times in seconds, so the units of the standard deviation will also be seconds. In E, we are told that the upper quartile Q3 is 23, and we need to use linear interpolation to estimate the interquartile range. Well, we need to first start by obtaining an estimate for the lower quartile Q1, and then we know that the interquartile range is simply the difference between Q3 and Q1. So to find Q1, we do a quarter of the total frequencies, which is 100. So this gives me 25, and I need to interpolate the value, the time corresponding to the 25th position. So looking at the frequency table we had, we can add the cumulative frequencies. So this is 10, 10 plus 16 is 26, 26 plus 24 is 50, then it's 85, and then it's 100. We know that the last value in the cumulative frequency line should be the total frequency. We're trying to interpolate the time corresponding to the 25th position, and the 25th position is between 10 and 14. So what we can do is simply draw a diagram here to help us set up the interpolation process. We're trying to interpolate between 10 and 14, and what we're trying to find is Q1. And we know that the last observation not to be included is the 10th one, whereas the last one to be included here is the 26th observation, and we're trying to interpolate for the 25th observation. So what I'll be doing is that Q1 minus 10 over 25 minus 10 is equal to 14 minus 10 over 26 minus 10. So let's write this down. Q1 minus 10 over 25 minus 10. So the small opening over the small opening is equal to the big opening, 14 minus 10, over the big opening of 26 minus 10. This leads to Q1 minus 10 over 15 is equal to a quarter. So Q1 minus 10 is a quarter times 15. And therefore we obtain that Q1 is 13.75. Remember, we're trying to find the interquartile range. So IQR is simply Q3 minus Q1. We have been given Q3 to be 23 at the beginning. So that's going to be 23 minus 13.75, which turns out to be 9.25. And that's also measured in seconds. In question 2, we've got two bags, X and Y, containing green and blue marbles only. Bag X has 5 green and 4 blue. Bag Y has 6 green and 5 blue marbles. So the experiment is to pick at random a marble from X and put it into Y. Then pick a second marble at random from X and place that in Y as well. And then draw the third time from bag Y. And we've got the tree diagram given here, and we need to complete it showing all possibilities. So remember, we are starting off with 5 green and 4 blue marbles. That's why the probabilities in the first branch are 5 over 9 and 4 over 9. Well, if the first marble removed is green, then this means that in the bag X we've got 4 green and 4 blue marbles. That's why we've got 4 over 8 and 4 over 8. However, if the first marble removed is blue, this means that we are left with 5 out of 8 being green and 3 out of 8 being blue. So this completes the removal of the 2 marbles from bag X, and we're now going to see what's happening when we draw the third one from bag Y. Remember that whatever we draw from bag X goes into bag Y. So we have added 2 green marbles into bag Y, which originally had 6 green marbles and 5 blue marbles. So it's now containing 8 green marbles, and the total went from 11, the 6 plus 5, to 13, so 8 over 13, whereas it still contains 5 out of 13 being blue. The second scenario is the green-blue scenario, so we have increased the number of green marbles by 1 and the number of blue marbles also by 1. So that means we're looking at 7 over 13 and 6 over 13. The blue-green marble is equivalent because we have simply added 1 of each. So this is still going to be 7 over 13 and 6 over 13. And just for confirmation, if we put 2 blue there, then we go to 7 out of 13 being blue and 6 out of 13 being green. In part B, we are asked to find the probability that the 2 marbles selected from bag X are of different colors. So if we go back to the tree diagram, this means we are looking for the green-blue scenario or the blue-green scenario. We don't really care about the draw from bag Y. So we know that we multiply the probabilities of the branches through which we travel. So I'll be doing 5 over 9 times 4 over 8 plus 4 over 9 times 5 over 8. So let's just do this calculation here. We have 5 over 9 times 4 over 8 plus 4 over 9 times 5 over 8. Put this on the calculator. You get an answer of 5 over 9. In part C, we need to find the probability that all 3 marbles selected are of the same color. So once more, if we go back to our tree diagram, we are looking at the green, green, green scenario or the blue, blue, blue scenario. So I'm just gonna multiply the 3 probabilities together, these 3 together, and then add them up, which means that we should be doing 5 over 9 times 4 over 8 times 8 over 13 plus the 4 over 9 times 3 over 8 times 7 over 13, and this gives an answer of 61 over 234. In part D, we are told that given that all 3 marbles selected are the same color, find the probability that they are all green. So if we just go back to the tree diagram for a moment, this is conditional probability. It is given that they are all of the same color, which means that one of these 2 happen for sure, and we're wondering what's the probability that it's the green-green scenario. So what I'll be doing is I'll be doing the probability of 3 greens divided by what I know for sure to have happened, which is the probability of all being of the same color. So this is conditional probability. We want the probability of green, green, green given all 3 are of the same color, which is simply the probability of green, green, green over the probability all being of the same color, where the green, green, green scenario is 5 over 9 times 4 over 8 times 8 over 13, whereas being all the same color is simply the answer we obtained in part C, which is 61 over 234. Put this on the calculator, you get 40 over 61. So in question 3, we've got the probability distribution of the discrete random variable x. It can take values 2, 3, or 4 with the corresponding probabilities shown here. A is a constant, and we need to find in terms of A the expectation of x. Well, we know that the expectation of x is simply found by considering the sum of the products of x with the associated probabilities. So I'm just gonna do 2 times A, which is 2A, plus 3 times 0.4, plus 4 times 0.6 minus A. So I will expand this to get 2A plus 1.2 plus 2.4 minus 4A, which leads to 3.6 minus 2A. This is the expectation of x in terms of A. In B, we're asked to find the range of the possible values of the expectation of x. So looking at the probability distribution, we know that A is a probability, so it must be between 0 and 1, and so is 0.6 minus A. So let's start by writing this. We say A to be between 0 and 1. We could put strict or inclusive inequalities. It's okay, both of them are acceptable. And also we want 0.6 minus A to be between 1 and 0. This means that we need A to be between 0 and 0.6. Now, when A is 0, the lowest value it could be, then the expectation of x, we can see it's 3.6. Whereas when A is 0.6, when A is the maximum, the expectation of x is simply 3.6 minus 2 times 0.6, which works out to be 2.4, and therefore we conclude that the expectation of x is between 2.4 and 3.6, and as I already said, it could be relaxed or strict inequalities. Both of them are acceptable here. In part C, we are told that the variance of x is 0.56, and we need to find the possible values of A. So I will actually start by finding the expectation of x squared, which is needed when we calculate variance. So the expectation of x squared is simply taking the x value, squaring and multiplying by the associated probabilities. So it's going to be 2 squared times A plus 3 squared times 0.4 plus 4 squared times 0.6 minus a, which leads to 4a plus 3.6 plus 9.6 minus 16a, which simplifies to 13.2 minus 12a. Well, we know that the variance of any random variable is given by the expectation of x squared minus the square of the expectation. We have that the variance of x is 0.56. The expectation of x squared is 13.2 minus 12a. And the expectation of x, we found this before, it's 3.6 minus 2a all squared. We will proceed by expanding. We get 0.56 is 13.2 minus 12a minus 12.96 plus 14.4a minus 4a squared. I will collect everything on the left-hand side to get a quadratic in a, so 4a squared minus 2.4a plus 0.32 is 0, and I'll be using the quadratic formula to determine the possible values for a. So we have that a is minus negative 2.4 plus minus negative 2.4 squared minus 4 times 4 times 0.32 all under a square root and all divided by 2a, which is 2 times 4. This gives answer for a being 0.4 or a being 0.2. You need to show your method here. You either try with factorization, but bearing in mind that the coefficients here are decimals, I would certainly opt for the quadratic formula, show the substitutions into the quadratic formula, and you obtain two possible answers for a. In question 4i, we've got a Venn diagram given here. A and B represent events, and P, Q, R, S are probabilities. We have that the probability of A is 7 over 25, the probability of B is 1 over 5, and the probability of A intersection B dash union A dash intersection B is 8 over 25. And we need to use algebra to arrive at 2p plus 2q plus 2r is 4 over 5. So let's start with the easy part. The probability of A is 7 over 25. Well, A is this part here, which means that we can write down that P plus Q is 7 over 25. Similarly, when it comes to the probability of B being a fifth, this means that Q plus R should be giving me an answer of a fifth. And finally, let's consider this expression here. A intersection B dash means in A and outside of B, which is this part here. And A dash intersection B means I have to be in B, but not in A, so it's the only B part here, which means that P plus R is equal to 8 over 25. So I've got three equations, I've got three unknowns, P, Q, and R. Notice that if I add the P plus Q, the Q plus R, and the P plus R, I get 2P plus 2Q plus 2R is equal to 7 over 25 plus 1 over 5 plus 8 over 25. And if you put the right-hand side on the calculator, this gives me 20 over 25, which simplifies to 4 over 5 as required. We are then asked in part B to find the value of P, Q, R, and S. And starting from what we have found in part A, that 2P plus 2Q plus 2R is 4 over 5, we could divide throughout by 2 to get that P plus Q plus R is 2 over 5. Going back to the Venn diagram, we know that P plus Q plus R is all of this, and S must be that number that makes the total probability 1. So if P plus Q plus R is 2 over 5, this means that S must be 3 over 5. In addition, knowing that P plus Q is 7 over 25, we can simply say that R must be 2 over 5 minus 7 over 25, and this gives an answer for R of 3 over 25. We can then go to the second equation over here. We had q plus r, so q plus 3 over 25 is equal to 1 over 5, and this means that q is equal to 2 over 25. And finally, to find p, we could go over here. P plus r is 8 over 25, so p plus the value of r, which is 3 over 25, is equal to 8 over 25, which leads to p being 1 over 5. In II, we've got two events, C and D, with the probabilities for C and D given in terms of x, where x is a positive constant, and we are told to consider the probability of C plus the probability of D to show that they cannot be mutually exclusive. Well, let's start by reminding ourselves that for any two events, C and D, the probability of C union D is simply the sum of the probability of C and the probability of D, and then deduct the probability of C intersection D. Now, when we say that two events are mutually exclusive, this means that their intersection is empty, so there is no chance that both of these events can happen. And therefore, if we are indeed looking at C and D being mutually exclusive, then we should have that the probability of C union D is the probability of C plus the probability of D, because the intersection is 0. So we have that the probability of C is x over x plus 5, and the probability of D is 5 over x. I could express everything over the same denominator of x brackets x plus 5, and we've got x squared plus 5 times x plus 5, which gives me x squared plus 5x plus 25 over x squared plus 5x, which can be written as x squared plus 5x over x squared plus 5x plus 25 over x squared plus 5x, which we can see is 1 plus 25 over x squared plus 5x, which is certainly greater than 1 since x is greater than 0. And this is not possible. This is a contradiction. We cannot exceed 1 for probabilities, and therefore we conclude that the probability of C intersection D must be greater than 0, and therefore the events C and D are not mutually exclusive. In question 5, we've got the lengths L millimeters of housefly wings normally distributed with mean 4.5 and standard deviation 0.4, and we need to find the probability that a randomly selected housefly has a wing length of less than 3.86 millimeters. So we need to find the probability of L being less than 3.86. We will use standardization to go to Z, so it's the probability of Z less than 3.86, and we deduct the mean of 4.5, dividing by the standard deviation of 0.4. This gives the probability of Z being less than negative 1.6. So we don't like the fact that the value here is negative, so it's going to be 1 minus the probability of Z being less than 1.6, and we go to the table of normal probabilities to extract the probability of Z being less than 1.6. Looking at the table for 1.6, the corresponding probability is 0.9452, and therefore we've got that the probability here is going to be 1 minus 0.9452, which gives an answer of 0.0548. In part B, we are asked to find the upper quartile Q3 and the lower quartile Q1 of L. It makes sense to start by drawing a bell-shaped curve. The center is at 4.5, the mean, and Q1 is that value that leaves 0.25 of the distribution on the left-hand side, whereas Q3 is that value which leaves 0.25 on the right-hand side. So to find the upper quartile Q3, we start by having probability of L being less than Q3 being 0.75, because the probability of being above Q3 is 0.25, so the probability of being below is 0.75. We will again standardize, so the probability of Z less than Q3 minus 4.5 over 0.4 is equal to 0.75. I will go to the probability table to extract the value corresponding to a probability of 0.75. So going through the phi of z, the probabilities, we see that the closest value for 0.75 gives me a z value of 0.67, and therefore we can say that Q3 minus 4.5 over 0.4 is equal to 0.67. I can cross multiply to get Q3 minus 4.5 is equal to 0.268, and therefore this leads to Q3 being equal to 4.768. For the lower quartile Q1, I could repeat the process. However, I strongly suggest we exploit the symmetry of the normal curve. So we have already established that Q3 is 4.768, and by symmetry, it must be the case that the mean of 4.5 is the midpoint of Q1 and Q3, which means that Q1 plus 4.768 over 2 must be equal to 4.5. This means that Q1 plus 4.768 is equal to 9, which leads to Q1 being equal to 4.232. We are then told that the value greater than Q3 plus 1.5 times the interquartile range, or smaller than Q1 minus 1.5 times the interquartile range, is deemed to be an outlier, and we need to find these two outlier limits. So we have that Q3 plus 1.5 times Q3 minus Q1 is simply given by 4.768 plus 1.5 times 4.768 minus 4.232, and this gives an answer of 5.572, whereas Q1 minus 1.5 times Q3 minus Q1 is going to be 4.232 minus 1.5 times 4.768 minus 4.232. Plug everything on the calculator, get 3.428. We then have that the housefly is selected at random, and we need to use standardization to show that the probability of this housefly not being an outlier is 0.99323 decimal places. So for this housefly not to be an outlier, it means that it lies within the two limits we just calculated. So the probability of not being an outlier is simply going to be given by the probability of 3.428 less than L less than 5.572. We will standardize both values. So this is going to be the probability of 3.428 minus 4.5 over 0.4 being less than Z being less than 5.572 minus 4.5 over 0.4, which gives values of minus 2.68 and 2.68. I will now split the double inequality. So this is the probability of Z being less than 2.68 minus the probability of Z being less than minus 2.68. The probability of Z being less than 2.68, I can extract this from the normal distribution table. However, for this one, I need to make sure that this is positive. So I can write this as a probability of Z being less than 2.68 minus, and I open brackets, 1 minus the probability of Z being less than 2.68. If we go to the normal tables once more, 2.68 is between 2.65 and 2.70. Well, it's closer to 2.70, so I'm going to pick the 0.9965. So going back to my calculations, this is going to be 0.9965 minus brackets 1 minus 0.9965, which gives an answer of 0.993 as required. And then in part E, we are told that given that this housefly is not an outlier, showing a working, find the probability that the wing length is greater than 5 millimeters. Once more, I will draw my bell-shaped curve. What we know for sure, it's conditional probability question here. We know for sure that we are not an outlier, so we are between 3.428 and 5.572. And we're wondering what's the probability that we are greater than 5 millimeters. So maybe 5 is here. So essentially what we need to do is calculate the probability shaded in red here over the probability appearing in yellow. So I will start by finding the probability that we are between 5 and 5.72. So once more, I will standardize both values. This is giving me the probability of 5 minus 4.5 over 0.4 being less than z being less than 5.572 minus 4.5 over 0.4. So this simplifies to the probability that I'm between 1.25 and 2.68. I can split the double inequality into the probability of z being less than 2.68 minus the probability of z being less than 1.25. So going once more to the tables, we can see that for 2.68, I'm going to pick 0.9965, whereas for 1.25, I will pick 0.8944. So let's write this down. We've got 0.9965 minus 0.8944, which gives an answer of 0.1021. This is the probability I'm between 5 and 5.572. We are after the probability of being here, given that we were in this shaded part. So the probability required is a conditional probability. The numerator is the answer we just found, the 0.1021, which is essentially the intersection in the graph, so this part here, over what I know for sure to have happened. I'm surely not an outlier, and the probability of not being an outlier is 0.993, which gives an answer of 0.10323 significant figures. In 6, we've got a research student investigating the maximum weight Y grams of sugar that will dissolve in 100 grams of water at various temperatures x degrees Celsius for x between 10 and 80, where the student came up with a regression line y is 151.2 plus 2.72x, and we need to interpret the gradient of the regression line, the 2.72. Well, we know that the 2.72 is the slope, it's the gradient, which means that for every extra increase in x, and x is the temperature in degrees Celsius, then we expect the amount of sugar that will be dissolving to increase by 2.72. So let's put this in writing. For every extra degree Celsius, 2.72 extra grams of sugar are expected to dissolve. In B, we need to use the regression line to estimate the maximum weight of sugar that will dissolve in 100 grams of water when the temperature is 90 degrees Celsius. So this is calling for us to just substitute x is 90 because x is the temperature. So when x is 90, y is 151.2 plus 2.72 times 90. The answer is 396 grams. Remember to include units. And then in part C, we need to comment on the reliability of our estimating, giving a reason for our answer. Well, if we read the question carefully, the derivation of the regression line was based on x being between 10 and 80. We have just estimated for x being 90. So we observe that 90 is greater than 80 degrees Celsius. So we are outside the range of observed data, and therefore this estimate is not reliable. It's called extrapolation, and extrapolation should always be viewed with caution. Part D, we are given some extra summary statistics shown here, and we are asked to show that the product volume correlation coefficient turns out to be 0.988. Notice that this is a 7-mark question. There is a lot of work involved. We need to use all of these together with the regression line in order to come up with the value of the product moment correlation coefficient. Let me start by reminding you that SYY is defined to be sigma y squared minus sigma y all squared over n, which in our case it's going to be 851093 minus 3119 squared over 12, and this gives an answer of 412.91667. Notice I'm quoting full accuracy here because I'll be calculating lots of quantities along the way. I want to make sure that I'm not going to sacrifice my final accuracy due to premature rounding errors. Now, we know that the equation of the regression line was given to be y is 151.2 plus 2.72x, and we know that this line passes through the point x bar, y bar. So we have that y bar is 151.2 plus 2.72x bar. Well, y bar is 3119 over 12, which is 151.2 plus 2.72x bar. We can solve for x bar. We get first of all that 6523 over 60 is equal to 2.72x bar, and dividing by 2.72 gives me that x bar is 32,615 over 816. I can use this to extract the sigma x. We know that x bar is found by doing sigma x over n, which is 12. So this is 32,615 over 816. Cross multiply by 12, we get sigma x to be 32615 over 68. So we've got the sum of the x values, and I can proceed in finding Sxx. So Sxx will be sigma x squared minus the square of sigma x over n. So in our case, sigma x squared is given to be 24,500 minus 32,615 over 68 squared divided by 12, and this gives an answer of 5329.400501. So we've got SYY, we've got SXX, and we also know that the gradient of the regression line, the 2.72, is given by SXY over SXX, which in our case is SXY over 5329.400501, which gives SXY, if I cross multiply, to be 14,495.96936. I've got all the quantities needed to calculate the product moment correlation coefficient. We know this is given by Sxy over the square root of Sxx Syy. So let's substitute the values we obtain. It's 14,495.96936, all of it over the square root of 5329.400501 times 4112.91667 and square root. Plug everything on the calculator, we get 0.98775 ... which of course rounds to 0.988 as required. And finally, we are told that the supervisor plotted the original data on the scatter diagram shown below, and with reference to both the scatter diagram and the correlation coefficient, we need to discuss the suitability of a linear regression model. So we need to assess whether fitting a straight line makes sense, and we need to make a reference both to the scatter diagram and the correlation coefficient. So first of all, looking at the scatter diagram, we can see that the points align roughly along a straight line, so I imagine something like that. And we have also seen that the calculated value for R is quite close to 1, 0.988. So this is evidence in favor of a linear regression model. So what we need to say is that since R is close to 1 and the points lie close to a straight line, then we say that a linear regression model is indeed suitable.